Hey guys, we're getting near the end of the semester. We're in chapter 19. This chapter is about thermodynamics. It's the second time in chemistry that we've encountered thermodynamics. Previously in 1211, chapter 5 was all about thermodynamics. The things that we learned in chapter 5, we definitely need to remember those things as we move into chapter 19. There will be a lot of relevant information. I'm going to kind of skim through the first few slides here. By the way, I've updated the PowerPoint. The newest version is in the shared class files, so if you have a chance to look at that before you watch this video, it may help you follow along a little bit better. I have made some significant changes. So we definitely know enthalpy of reaction. We're talking about delta H there. It's the change in the internal energy of a system as it undergoes a reaction. State functions are properties of a system that their value does not depend on how you get to that state that you're in. For instance, the internal energy of a system, if you take energy out, put energy back in, take it out, put it back in, it doesn't really matter how often you change the internal energy, how much you take out or put in. You measure the raw amount of what's in there. That is a state function. Another idea is like altitude. If I travel from where I am now to the top of a mountain, I can measure the altitude change in my position, and that is a state function. It does not matter how I got from where I am to the top of the mountain. I might have hiked straight up the mountain and have a very direct route. I may take a winding trail that has switchbacks back and forth, so the total distance traveled is not a state function. But if I just measure the altitude where I started and the altitude where I finished, the difference in those two values tells me my change in altitude. Okay, I could have even hopped on an airplane, flown way up, well above the top of the mountain, and then landed on top of the mountain. Again, my change in altitude just depends on the final position minus the initial position. Those are state functions. Just remember, negative delta H is exothermic. We need to know energy is the ability to do work. Work is force times distance. Our first law of thermodynamics is the law of conservation of energy, which states that the energy of the universe is constant. The change in energy of the universe is always zero. So basically, if a system loses energy, that means that the surroundings must be gaining the same amount of energy. We have to conserve the energy between the system and the surroundings. We also talked about the change in energy system. There are two ways that a system can gain or lose energy. That can be just through the absorption or release of heat, or it could be by doing work. Move on. Some of our basic ideas. When a system absorbs energy, that's a positive Q value. If a system releases energy, it's negative. If a system has work done on it, that means the surroundings are putting energy into the system. That's positive. And then if the system does work on the surroundings, that means the system is expending energy out to the surroundings. That gives me a negative work value. Again, these are just general concepts. We're not going to use them a lot in most of what we do, but it's important to be aware of our main ideas. Finally, again, work is force times distance. So delta H, when we calculate delta H's in 1211, there's several different ways we calculate it, but our probably main references, if we look in the appendix, we can see for a given reaction, we sum up the heat of formation values of the products, we subtract the sum of the heat of formation values of the reactants. We have to remember the stoichiometry here, where if a reaction is making 2 moles of water, then I have to look up the heat of formation value for water. I need to know what physical state it is, either solid, liquid, or gas, because the heat of formation does depend on physical state. But I look up the value I need, and if there's 2 moles, I'll have to multiply that value times 2. The numbers in the appendix are always correspond to 1 mole, but then you have to multiply by the coefficient if needed. If we are under standard conditions, that means that we're going to use the delta H. We're going to put the not symbol, which is a superscript circle. Standard conditions means in thermodynamics, it means that we have a partial pressure of all gases. So each gas has its own partial pressure of 1 atmosphere, and then anything that's in solution, the concentration of all things in solution must be 1 molar. If those things are true, then that's when we have standard conditions. There'll usually be a temperature provided also. So we say standard conditions at 25 degrees Celsius or standard conditions at 0 degrees Celsius. So when we look up the standard enthalpies of formation, again, these are tied into standard conditions that we are looking up. So, whole point of this chapter, we bring in all the stuff that we know about delta H and Q, the energy changes in the system, but we now want to apply those concepts to, when we look at a reaction, we want to know, is that reaction spontaneous or is it not? When we say a reaction is spontaneous, we're asking, is it going to occur on its own without us having to do anything extra to make it happen? So a spontaneous process will occur without outside intervention. It has a direction. If I say a process is spontaneous, I typically am referring to the forward reaction where I have reactant molecules that are going to turn into products. If the forward reaction is spontaneous, that would imply that under those same conditions, the reverse reaction is not spontaneous. Okay? So only one direction can be preferred at a time. If the forward reaction is not spontaneous, then that implies that the reverse reaction is spontaneous. Okay? Now, which way is spontaneous? This does bring back our equilibrium concepts that if we look at the concentrations of reactants and products, if we calculate Q, if Q is greater than K, that means the reaction is going to shift to the left. That would mean that the reverse reaction is favored. That is the reaction that would be spontaneous. If Q is less than K, then that means the reaction should shift to the right. That's the forward reaction. So if Q is less than K, then the forward reaction would be spontaneous. So if we ask the question, will ice melt? If I have a flask with frozen water, will it melt? Yes or no? Is it a spontaneous process? Well, there are 3 factors that we need to think about. First of all, the delta H. If a reaction has a negative delta H value, so it's exothermic, it is much easier for a process to occur if it is releasing heat to the surroundings. It's difficult to get a process where energy has to flow into the system. That kind of goes against a lot of laws of thermodynamics. So it's harder to get an endothermic process to be spontaneous, but that's not the only factor. We have endothermic or exothermic, which is delta H values. We're going to introduce entropy in a few minutes. That's going to be S is entropy, or delta S is the change in entropy. And then finally, temperature is also a factor. Okay? So if I look at the freezing or melting of water, we all know that if ice is below 0, then the freezing of water will be spontaneous. If the temperature is above 0, then the ice will melt, so melting is going to be spontaneous. So the spontaneity of your reaction depends on delta H and delta S, but it also has a temperature component that has to be factored in. So we need to talk about entropy. Entropy is the level of disorder in a system. We're going to start out with kind of an example of, okay, if I have a container where I have one side of the container, or this would be called a round bottom flask, it's filled with a gas. I have another flask on this side that is evacuated, so it has nothing inside of it, and I have a valve in the middle. If I open the valve, what happens? Well, basically, some of the gas from the right side will pass through the valve and get to the left side, and we're going to end up with some of the gas on both sides. And what we will notice is it's pretty much spontaneously going to go to the point where the pressure of the gas on each side are going to be about equal. Why is that? Well, the simple answer is, when we think about entropy and disorder, we say that right now in the upper system, all the molecules are on one side. That is a level of organization that the molecules don't all want to be packed into one container. So as soon as you open the valve, the molecules want to spread out. get into the other container and have more space. By spreading into more space, that is more disorder. Okay? By saying it that way, where the molecules want to escape, we're giving the molecule feelings and desires, which is not really true. Actually, the reason the molecules do this is not so they can get space. It's actually just based on probability. If we have a lot of molecules that are free to move, so when we open the valve, if the molecules have the freedom to spread out, the more space we have, if I just randomly throw the molecules up and let them go wherever they want, there are a lot more possible arrangements that can occur where the molecules are spread out than there are where all the molecules are all pushed to one side. There are very few arrangements possible where all the molecules stay on one side of a container. There are many more possible arrangements where they spread out. We'll move to the next slide and we can talk about that. So, entropy is a measure of disorder or randomness of a system. It's a thermodynamic function. It basically describes the number of arrangements, which that's what I was talking about with when I have a gas and I open it up. I have, with a larger container, I have many more possible ways to arrange the molecules. Okay? In some discussions, they refer to each arrangement as a microstate. Like if I put all the molecules in one place and freeze the system and look at what I have, that one arrangement is called a microstate. There are a huge number in a gaseous sample, so go back to the previous slide. If I have one atmosphere of gases, there are just millions and millions or even trillions or quadrillions of molecules in this container. If I let them go wherever they want, I'm going to get not an infinite number of arrangements, but approaching an infinite number of arrangements that I could have. And most of those arrangements are going to have the molecules spread out across the whole system as well as possible. So, when we say that nature spontaneously moves toward disorder, really what we're saying is nature spontaneously will proceed toward the states that have the highest probabilities of existing. Okay, so imagine I walk into my bedroom and I have a stack of clothes sitting on my bed and they're all nicely folded. If I pick up the stack and just throw it up in the air, everybody knows that the chances of the stack landing folded perfectly back on the bed is almost zero. It's not zero, but it's approaching zero. It is very unlikely that the clothes would land on the bed as organized as they were before I threw them up. It's even less likely that they would become more organized. Like maybe the stack could be folded even more perfectly than it was before. It could happen, but it's unlikely. It's much more likely that when I throw it up, there are many more arrangements where the things get scattered randomly. And imagine I pick the pile up and throw it up 3 or 4 times in a row. Every time the pile lands, it's going to become more disordered. Why is that? Well, it's because there's a much higher probability that each time I throw it up, the clothes can move out in new and different ways and become less and less organized. So entropy is purely a probability concept. It has nothing to do with nature wanting to be disordered or anything like that. It's just probability. So same idea. This is a smaller system. If I have 4 molecules on one side of a container, but I let them move freely, I could have, there's only 2 possible arrangements where they're all on one side. Either they could all be on the left or all be on the right. Those are the only 2 microstates where all the molecules are on the same side. If I put 3 molecules on one side and 1 on the other, and if I labeled the molecules like A, B, C, and D, I could have A, B, and C over here and D over there. I could have A, B, and D here and C over there. I could have A, C, and D here and B over there. All these are different arrangements I could have. I could have a good number of arrangements of arrangement 2 here, but then if I go to arrangement 3, if I calculate all the different possible arrangements, I'm going to have a lot more arrangements of possible combinations that give me arrangement 3 than I do arrangement 2, and I have a lot more arrangement 2 than arrangement 1. So chances are, at any point with these 4 molecules, most of the time, the system is going to look something like this. The more molecules I introduce, the more the randomness is going to shift, but it's going to favor a system where I'm going to have nearly equal molecules on both sides, because that arrangement statistically is going to be preferred well above the others. That's why in the slide, a couple of slides ago, when I looked at the gases, it ends up being about 0.5 atmospheres in each container, because when I'm dealing with billions and billions and billions of molecules, it's probably going to end up having pretty close to half and half on each side all the time. Because if a few molecules go through this way and a few go through that way, with random motions, with large populations, we're always going to end up averaging out and have pretty equal to the same pressure on both sides. So basically, if we start out with our system in arrangement 1, if we give it a little bit of time, chances are at any point later, if we look at this system, it's probably going to be in arrangement 3 most of the time. All right, so I'm going to go ahead and cut off the video. We'll start up with another video in just a second.